thing statement because how explicit is a bit unclear, and there are many issues involved in this. Yeah, so okay, so E always supports a variation of Hodge structure. Any E is always a variation of Hodge structure, and then this has okay, you need to generalize Deligne slightly to deal with that case, but then this has a mixed Hodge structure like that of a pure variety. In the trivial case, trivial local system, it's Deligne's construction. Otherwise, it requires a little work. It would requires Saito's results or something weaker than that. Okay. The Galois representation, of course, is clear. Okay. So right. So I'm already fudging here because the Galois representation requires that the coefficient system comes from geometry in some sense. So I'll just assume that. It's conjectured to always, but that's very hard. So assuming E comes from geometry. E comes from geometry. Okay, so E is motivic in some suitable sense, but it's conjectured that all the homogeneous local systems on Shimura varieties are motivic, but it is far from being accessible. Okay, so the question is what, I'm going to state some, or discuss a general approach to this question. So of course, as I said, Harder and many people following then have studied this since, let's say, the 80s and 90s. And certainly some interesting examples have been found, but I'll try to say how the approach that we are trying to do, how it will differ and what one can say. Okay, so that's the mixed structure. So what about automorphic forms? So I'm going to assume that everybody knows what automorphic forms are. So let me again, so I'll write this as A. So this is the GK infinity cross GAF module of automorphic forms. Okay, so I'll just say what these are. They are smooth, uniform, moderate growth, K finite for the GR, K infinity finite, sorry, and finite for the center of the universal enveloping algebra. Okay, so this is a big module. I'm not assuming L2, right? So this is important. And a basic theorem, which is due to Franke and was appeared in 1998, I think it was proved maybe 10 years earlier, is that this thing, okay, so I'll emphasize that at least I have to tensor it. See, we have a good transcendental description of this space, okay? Namely, it's the GK cohomology of this space of automorphic forms tensored with E, okay? And I will actually reduce to the space of automorphic forms with generalized infinitesimal character theta, where theta is the infinitesimal character of E check, of the contragradient of E, which in terms of the Harshchandra's parameterization of infinitesimal characters would be the highest weight of E check plus rho and this orbit, okay? Okay, so just standard things. And this is generalized infinitesimal character, meaning finite under the kernel of theta. Okay? So this is finite under kernel. Okay, so this is maybe a very strong Hodge theorem of an analytic type, because it's telling you that cohomology classes, at least with C coefficients, have representatives which are automorphic forms. Okay, so Franke also introduced filtrations of the space of automorphic forms. Okay, so henceforth I'm only going to work with A theta. Okay, and this is an important thing that I'm going to describe now in terms of the exponents, in terms of exponents. Okay, so let me just say what that means. So given an automorphic form and a parabolic subgroup P, one can take its constant term along P, okay? And the constant term itself can be, so P is MAN, okay? Let's see, maybe I should write MP, AP, NP just to be safe. And I can take the constant term, which is an average over n, and I can Fourier expand along AP. Okay? So let me assume now that G is actually semi-simple so that I don't have to, so I don't get notational problems. Okay. Okay. So what form does this take? This takes something like this. Okay, and I'll explain the terms here. Okay, so this is an exponential. This thing is a polynomial times an exponential on APs. So symmetric algebra of AP dual tensored with maybe functions which one might call automorphic forms, but I'll just write it in this. Maybe AP R0. Okay, the usual space. And so the point is that the Fourier expansion has the form of a bunch of exponentials times polynomials times some function which is like, so this is like a automorphic form on the Levy. Okay, so the set of lambda appearing in this are called the exponents, the P exponents. Okay, so given the P exponents, so the set xp, the P exponents of f are the lambda which are in AP star, okay, such that fp lambda is not 0. Okay, so there is this standard thing that given an exponent you can look at the real part of, okay, so I mean this is known to people, so I'll just mention that you can, we fix once and for all a minimal parabolic, and then we consider all these functionals as actually living inside the space of functionals of the minimal parabolic, the standard thing for those who are familiar with root systems. So then one can take the following thing, the real part of lambda plus, which is the projection of exponent to the Weyl chamber, the closed positive Weyl chamber. So I fixed a P and all that, P naught, minimal parabolic, etc. I should have said that, but let's say, and P is standard, so I'm maybe P naught, this is minimum. Okay. So what is the point here? So let me just draw a picture, schematic picture. So we have like this. We've projected all our exponents appear all over the place. Okay. So the point is, okay, so a very elementary fact is the exponents in, okay, so maybe I'll write it this way. So I can take theta. So now I'm going to look at automorphic forms of infinitesimal character theta, and theta plus means, again, I do the same thing. I project everything to the positive cone. Okay, so theta plus is equal to, and the point is this is exactly the same set of things that you get if you run over exponents. F in A theta. I'm just saying in a complicated way that the exponents of the forms in A theta are actually controlled by theta plus. Okay, so theta plus is a bunch of points all over the place, and then I project them all to the positive Weyl chamber, this, like this, like this, like this, maybe some number of things like that. And then I will just, so the natural thing is now I can multi-filter it by, or I can filter it as follows. The first step of the filtration, or it'll be the last step in my numbering, is that the exponents should lie. This is an equality, but it's just take all the elements of theta, project them to the positive Weyl chamber, and that is theta plus. So I'm using it for a set of things rather than a single one.
Theta is just it's just a bunch of points.
It's a bunch of points, and I project them all to the positive Weyl chamber. And those are the possible projections of exponents of f anyway. Okay. So maybe, yeah. So right. So I'll filter this according to the. Okay, maybe I should use one more color which I don't have. I'll just use white. It's not very visible. Okay, this is going very slowly. So the exponents are, maybe more symmetrically distributed of an automorphic form, and based on where the exponents lie, I will filter it. So namely, that I will say that the one step of it is just all exponents are what are called subunitary, and then I can choose some other way to do it, like that, and I can choose like that and like that. Okay? So choosing, so you see there are choices. So choose an indexing function, which I'll say call t theta plus to the integers, and define fp of a theta is f such that all exponents have okay. So let me just say what it is schematically, because there's kind of no point in going through this thing. So one filtration could be that everything with exponents in minus the positive cone is f naught. Then this is f, so I apologize for my numbering, but it's necessary, f minus 1. Maybe this is f minus 2 and this is f minus 3. Okay? So this gives me a decreasing filtration. So you see there are choice. So these are called the Franke filtrations. Okay, so I have not, so the indexing function has to have the property that t lambda is less than or equal to t mu if lambda is greater than or equal to me. Okay, so that's just so that everything is consistent. I'm not going to labor the point. So this gives a spectral sequence. So now I've filtered the space of automorphic forms, and Franke's theorem tells me that automorphic forms compute the cohomology. So I get a spectral sequence, something like this, let's say, which is E1, and it has, so it has the following shape. And it converges to what I want. Okay, so there is already a slight inaccuracy, because if I want to fix a level here, then I should fix a level for my automorphic forms. So I'll just pretend like this computes not pretend, it's true. This computes the direct limit over all k of that thing. So this is computing that. Okay, so I'll erase this now. I think I do want HP plus Q. Oh, sorry. Yeah. HQ, yeah, thank you. Okay, so this, I'll just say, okay, I'll be saying this later, so I won't say.
Sorry, Ft of theta is a space of automorphic forms?
Yes, and it's stable under GK and GAF. Yeah. So it's imposing conditions on exponents, it clearly commutes with GAF, that is not affected, but it continues to be a GK infinity module, yeah. Okay, so an informal statement of, maybe an informal version of the theorem, of a theorem I'm going to state, is that all these are spectral sequences in categories in mixed, okay, so I'll just say mixed structures, which one has to be a little, okay, so that means in IE, MHS, Galois representations over E, and actually mixed realizations over E. This is Deline's category of mixed, Deline and Janssen defined a category of mixed realizations, where basically it's a combination of these three and everything is tied together properly with isomorphism. Okay, so this is an informal statement of the theorem. I'll give a more formal statement of the theorem. But let me point out that as it stands, the way this theorem is stated, it's stupid, because as somebody pointed out to me once, proving that a vector space has a mixed Hodge structure is, well, every vector space has a mixed Hodge structure, because there's a trivial mixed Hodge structure. It's not like having a Hodge structure where at least some parity of dimension is forced. So everything has a mixed Hodge structure, in particular 0 works. So if one is saying something, one has to say something, it has to be natural, etc. So then the question is, how do you get mixed structures on these things? Okay, so I'll explain how that works. So that it requires a little more sophisticated machinery. Are there any questions at this point, or should I stop? Okay. Okay, so the basic approach to this thing uses a construction of, construction of Sophie Morel around 2000, I think it appeared around 2008, a few years earlier. So she defined what are called weight truncations in categories of mixed sheaves, okay? I'll just remark that the ordering of these is exactly like in the Langland's quotient theorem. I mean, you're considering exponents exactly like in the local case of the Langland's quotient theorem. But the proof that this gives a well-defined filtration is quite hard. I mean, Franke had a lot of work to do, right? Okay. So I'll just say what I mean by this, what I mean by categories of mixed sheaves, but I emphasize that they can be used as a black box, and they should be. So I'll write script M is a, I don't know what the correct word is, but let's say varieties over, let's say, E, which is a fixed field. You have to fix an embedding of E in the complex numbers. In our case, actually, Shimura varieties come with an embedding, so there's no problem. And let's say this is an assignment from, for every variety, you give me an abelian category of some kind, and it has the following properties. Abelian category of objects, so I'll write some examples here in a moment. And there is more. For the point is there is some functoriality for f, x, and y in varieties over E. There exist functors between the derived categories, bounded derived categories. So again, I'll just say one just has to accept these formal properties because what I'm going to say next kind of doesn't depend on them. Yeah. Sorry? So the E is the reflex field and it's also the coefficient system, but it's always clear from context. So I'm not going to change the notation. It'll cause me trouble. Sure.
It's hard to show that this is a filtration, but I don't understand.
No, it's obvious that it's a filtration. Sorry. So how you describe the subquotients is hard. Yeah, sorry. That's what I meant to say. I'm going to use maybe use that later. Yeah. I mean, this kind of contains the theorem, which was an important theorem of Franke, that every automorphic form is appears in the Laurent series expansion of some Eisenstein series at some point, which was an important result, right? Now maybe there are other proofs of that. Yeah. Okay, so there is a functorial formalism for objects, right? Right, and there are these four functors, whatever they are, right? So these are already derived for those who are interested. And there is a forgetful functor on any variety to, okay, so again, this is another black box, but it'll become clear why I need to use this black box in a moment. So let's say perverse sheaves valued in, it doesn't matter where, rationals, okay? So let me just mention that why this is of interest to us, perhaps. Okay, and the functor derives to a functor between these abelian categories. Derived categories of these abelian categories. Derived category of M is just derived category of M, and the derived category of perverse sheaves is the category of constructible sheaves. So this is actually a deep theorem of Bailenson. Okay, and moreover, I'll just say it: all these functors under the the forgetful functor, they go over to the traditional functors on sheaves. So these functors were defined here, and they go over to the traditional functors on sheaves. Okay, so this is. Yeah.
You say that the construction of this sequence makes sense for the more of the
Yes. I'm going to explain why. Yeah. So that's maybe in some sense maybe the somewhat interesting thing, right? So yeah. Although I'll say that even that it makes sense in Hodge structures is really not clear at all, and you'll see that. So okay, maybe I'll take a moment to make a remark that in this description you can see the Hodge filtration quite easily. It's the naive thing, namely you break up G mod K into P plus and P minus. But the weight filtration is extremely mysterious. It is not given by some simple filtration on the space of automorphic forms. So if you're going to put a mixed Hodge structure on, say, things, you have to do it in some indirect fashion, and so we'll use a lot of geometric things, right? Yeah. In some sense, that is really the big question. Right? What can you say about the weight filtration? But okay, maybe it's not. Okay, so then there's duality. I won't live. Everything works as you would expect, and the most important thing, which is of fundamental importance, is that there are weights, okay, on objects in M. Okay, so I'm going to just give you examples, and so if you're familiar with at least one of the examples, then all these statements you'll be able to write down the rest of the properties. So examples. So one is M could be mixed Hodge modules of Saito. So this is purely the Hodge theory. Another one, okay, so I'm going to lie here, but another one could be mixed Étale sheaves. Perverse. So the point is, it's important to note that this is the perverse T structure here. Okay, so this is not quite treatable, I'll say. This is almost an example, but it's not quite. It has the properties I've listed here, but then there is actually, okay, so you can add de Rham rational structure here when your variety is defined over E, and you can look at mixed Hodge structures over E, so to speak. And there is a category of mixed realization sheaves which contains puts all these together. It puts the Hodge realization and all the Aladic realizations and all the comparison isomorphisms you need together, and you can show that there is a category which has all the properties you want and which has stabilities, etc. And over a point, I'll just say this, I want this thing. This is roughly mixed realizations of Deligne. It's slightly stronger, but so this is approximately, okay? So the point is, one can behave with these objects and do functorial things with these objects as if you have everything you want, okay? And it's important that we are working in characteristic 0 over a number field embedded in C, and that allows you to use comparison isomorphisms to tie these things together. Of course, none of this is my is work of mine. This is all essentially due to Morihiko Saito. Okay, so yeah, okay. So the fact that there are weights allows you to truncate, define a thing, and this is Morel's idea. So maybe this, so far I've only talked about Saito's thing, but this is Morel's idea. Which is that you can, okay, so now if you want to truncate stuff, I already said the word truncation, you need to construct some subcategory and an adjoint, or put another way, or ideally a T structure. So Morel defined new T structures. I'll give you the definition on, okay, so I'm going to simplify notation by just writing curly D for the derived category. Although I will continue to use M also occasionally, using weights. Okay, so I'll define the T structure. So the T structure will be depending on an integer in the integers, A and Z, and this will be, so this is meant to indicate that it has something to do with weights. And then D is the category, derived category over there, and A is the integer. And this is simply objects in D, complexes in D of X, such that the cohomology objects have weight for all I. Okay, so let me write for all I, HI has weights less than or equal to A. Okay, and the other part of the T structure, just let me write this and I'll answer the question. Sorry, tell me. W is just a symbol so that we remember this T structure comes from weights, because otherwise there could be a confusion. Yeah, okay. So one thing I should point out, these are the homology functors which go into M from this derived category. So in some sense this is a perverse version of things, okay? They're perverse weights on the perverse realization. Now the classical Deligne purity of a complex, for those who know what it is that HIK has weights less than or equal to A plus I, and HIK has weights greater than or equal to A plus I. So this is shifted in some sense, or it has a different flavor. Okay. So, okay, so if I work in this category, Saito's Hodge theory tells me I have weights. Yeah? If I work in the mixed category where I use all the things, I can actually use both either Frobenius weight or Hodge theoretic weight, but then I have to appeal to some theorems to say, I have to appeal to Deline's purity theorem in the end to say that they're all the same. Okay? But everything can be, you can use either Archimedes weights, yeah, you can use either one. They're all consistent. So I should say the hard part here is in showing, I mean it's a very hard part, is in showing that once you make the definitions, all these functors preserve being mixed. Of course F lower star is the hard one, and that everything ties together consistently. So that Saito has understood this in the early 2000s. Okay, so this is a T structure. For any A. Okay. Now, okay, and the curious thing about this T structure is that both the upper and lower half are triangulated categories, stable under shift. So this is a bit unusual, at least at the time maybe it was a bit unusual. Now there are many T structures, exotic T structures known on various categories, but yeah, so they're stable under shift. That's a bit odd, but okay. But that's immediate consequence of this definition, that it doesn't matter which I you took. Okay, so now I'll just quote another piece of this thing. So these give a filtration. Okay, so I'll put this in quotes of, okay, so let me come back to my setting now. So now my setting is back to, I have M or MK, I'll drop the notation, and this is a quasi-projective variety, and I have a canonical way to complete it, and this is known as the Satake, Bailey, Borel compactification. So this is constructed by, in great generality, by Bailey and Borel in 1962. Okay? So this is a fundamental thing, and more or less all appears in all discussions of the geometry of these things at infinity. And this gives me a filtration, a way of filtering this direct image. Okay, so I recall I had a local system. I'm thinking of it as now, okay, I'm going to put an M here, means I'm thinking of it as a mixed sheaf. I'm not going to write down what the notation is, but it gives, I'm assuming I'm lifting it to an object here. Right, my M is here, I assume I lift it here. Okay? I discussed earlier when that is okay. And you can write the following things. So maybe I should just, okay, I'll explain what these numbers are. Sorry, is that my phone? Oh, okay. Okay. So, I didn't say one thing, sorry. Okay. So you have a T structure which we will think of with a varying A. So we'll think of this as a way of filtering the category, because as you increase A, these are all subcategories, and eventually as you increase A, you get the whole triangular category, or in this one, if you decrease A and make it more and more negative, you get the whole triangular subcategory. Now these inclusions, more or less, because they're part of a T structure, they have adjoints. Okay? So I'll denote, these are the important point. I have a truncation functor which goes from the whole D to the bottom half of the T structure, and I have another truncation functor which goes from D to the top part of the quotient, so to speak. Okay, so these are adjoint to the inclusions, adjoint to inclusions. Okay, so the usual thing, right? I mean, when you have a T structure, you can truncate. So now I will apply these functors in this setting. So I take, okay, so this number is important. So W is the weight of E, which if I had been smart, I would have taken to be trivial and I would have made E the trivial representation. D is the dimension of M. Okay, and then I take this WD plus 1, and eventually I know that I will get to the whole thing. Okay, so this is just a diagram of objects and morphisms in the category D. However, this behaves very much like a filtration, except of course derived category not being abelian, you can't talk about filtrations, and this is part of what's called a Postnikov tower. So this is just some formal gadget. We don't care too much about it, so it's part of a Postnikov tower. Postnikov tower. Postnikov system, sorry. But the relevant point is it gives a spectral sequence by some just general gadget. Converging to the cohomology HP plus Q of M, J, M lower star, J lower star E, which is just the cohomology that I want to compute. Okay? And the point is that more or less in any in the category M. Okay, the spectral object is in the abelian category. Okay, so so you'll ask me about the P plus Q. This is the right indexing. Okay, I'll just say that. Actually, I'm sorry, I agreed with you there, but actually this is the right indexing. Okay, so there are reasons to index it this way, and I'll explain what's going on. Okay, so there is a spectral sequence like this, and maybe the more precise theorem. Okay, so this is a precise theorem, but this is a special case of that case because I am treating one particular filtration, okay, which I'll tell you about later. Okay, so these two spectral sequences are Hecker equivariantly isomorphic and canonically and all those words from E1 on. Okay, so this is a precise version of the previous theorem. Okay, so let me remark something about this thing. You can ask, and what is the E1 term? So the edge term. This is the edge term. Okay, and the edge term has two descriptions. One is as HQ of GKL2 discrete of GA mod GQ. Okay, so I'll use a notation that people have used. Okay, and the other guy has the description IHQ of M coefficients in E, M star coefficients in E. So I should have said that I'm filtering things so that this first object, this is an important fact, and is the IC complex, for those who know what it is, on M star. Okay, and this is a theorem of Morel. In fact, this is somehow the main reason she introduced these functors. So to put it clear again, the bottom step of the truncation is the intersection complex, and then I'm truncating it by larger objects. Okay, I mean I'm filtering it by larger objects. The bottom step of this filtration was automorphic forms with subunitary exponent, and it's a fact that computes the L2 discrete spectrum cohomology, and this is also known for a long time, right? This was the Zucker conjecture, this identity. Okay, so sorry.
Graded pieces are supported on the boundary.
Yeah, so right. So the graded pieces are actually, so here this is very nice. The graded pieces are sums of pure intersection complexes supported on the boundary, and they're sums. It breaks up as a sum. Okay, so there's no extension data in the E1 term of this spectral sequence. So you can really hope to, that simplifies life, one hopes. Okay, so since, okay, so I have about 15 minutes, which means that I have to make some choices. Okay. Okay, so some of you may have, I have spoken about this result in some sense before, and in fact I've known some version of this result for a long time, but that's why I underlined Hecker equivariantly. That was kind of really a problem. So then for those who like these things, the problem is that one spectral sequence is defined by some sort of a very functorial a truncation in a T structure. This is obviously defined in some completely different way. And so at some point you lose track of what's happening with quotients. And because of the non-uniqueness of the cone and triangulated categories, it's very hard to deal with this. I did not do it, and prove this. So I should remark, what does this mean? So as I stated, the filtration, the first spectral sequence, which unfortunately I erased, obviously is a spectral sequence of Hecker modules because GAF acts. This spectral sequence, the point is that the action of Hecker correspondences exists by cohomological correspondences on this. So it's given in a very indirect way in the derived category. Okay? So this is also a Hecker GAF spectral sequence. And identifying those, because one is concrete and one is extremely, this thing turns out to be a big mess. And I had planned to explain how one gets around that, but maybe.
I'm sorry, the action of the Ferro group of the Franker spectral sequence now is deduced from this.
Yeah, so now you forget Franker spectral sequence and you take this spectral sequence. It's in the category of mixed objects. It happens that when you tensor C, it's canonically and Hecker equivariantly identified with the Franker spectral sequence. Okay, so this is an enriched version of that. So okay, so I mean, I really not sure how much time to spend on this. Okay, so let me just make some remarks. I'll make them aloud so I don't have to write. So first of all, as I said earlier, there was another approach. The traditional approach uses an embedding of M inside what's called the Borel-Serre compactification and a spectral sequence abutting to the Borel-Serre boundary. And this was, I think, introduced by Borel and maybe Harder. I'm sure. But anyway, Harder has used it a lot. And one produces extensions, tries to understand the standard exact sequence like this. And here we have a spectral sequence abutting to this, and then goes onwards and constructs sections using Eisenstein series. So as I see, this spectral sequence is, why should one prefer this? Because the intersection complexes are the fundamental thing here. This is more compatible with sort of, middle extension philosophy and all. It's also in some sense more compatible with Arthur's conjecture, because as I said, these, if you translate them back into analysis, the E1 term is a sum of L2 automorphic spaces on levies. And Arthur somehow gives you in principle, a direct description of those spaces. This is a bit disingenuous because you are going to end up stuck trying to understand the map from the L2 discrete cohomology to that, and so it basically reduces you to this problem, which is a difficult problem. Many people have worked on it. I think Birgit Spey has in recent years done some things to do with it, and earlier Franke and Harder and all these people. So, right. However, what I'd like to say about this is that if you want to study a Hecker isotype, so you fix a representation of GAF and you want to study a Hecker isotype. Of course, here I've taken the limit maybe over K, co-limit, and then this spectral sequence sort of gives you control over the whole thing, whereas the earlier approach usually dealt with examples. Okay, so that's not really what I wanted to say, so I'll say more about that if there are questions. Okay, so I'm sort of stuck between giving a couple of applications or telling you why. Of course, I'm obsessed with this equivariantly because that's what, it took me a long time to figure it out. And there is a very, what I think is a very elegant formulation of a theorem which implies this. So let me just go ahead and do that, yeah? And then I'll come back to the other applications. So the point is that, as I said, we want to, this spectral sequence is coming from a T structure. That spectral sequence is just coming very naively from a GK module and its filtration, and a GK cross GAF modules. So why are these kind of the same? So there is an important notion, of L module. So I'll formulate a theorem and then tell you what this thing. So this was formulated by Les Saper around 2006, okay? And they're a sort of combinatorial gadget which allows you to introduce a certain other triangulated category which is well related in the end to Franker's spectral sequence. You can relate, let's say, okay? So I'll tell you what they are and formulate a theorem which I like, which implies this, and then come to applications of this, okay? So, in some sense, it's in realizing this that maybe, before that I was a working class mathematician in Dinakar's formulation, but then now one was able to use some DG ideas, so one feels a little more this thing. Okay, so what is an L module? So for every parabolic, which I'll write as LP UP, parabolic, I give myself a graded vector space. So this is a graded L module, LP module. And this is for all parabolics. So let's say P equals rational. Of course, everything, I'm always working with rational parabolics. And this is the first datum. And the second datum is sort of the key point, is that for all P in less than Q in P, I have a mapping FPQ from H, the Lie algebra homology of UP mod UQ of EQ to EP shifted 1. Okay? Yeah. What is a? LP is the Levy, so algebraic finite dimensional representation of LP, graded algebraic finite dimensional representation. Yeah, so, okay. Okay, so what have I written here? So I'll explain this. So for every pair P inside Q, we have a +1 morphism from, this is the relative the Lie algebra cohomology for unipotent radical of P mod unipotent radical of Q with values in that graded, everything is graded, right? This is also graded, and it's a +1 morphism. And the property they have is that for all P less than or equal to R, the sum over Q between P and R of a certain PQ, I'll explain this in a moment. Okay, so let me explain what, maybe pictorially what this is, okay? So I have, for every P, this is the poset of parabolics, I have an EP here for P, I have an ER here, okay, which is a graded module, and I'm saying that for every Q lying between E and R, so these are the Qs, you take the obvious composition of this morphism with, for each pair like this, there's one morphism here and one morphism here which you can do. To make it compatible, you have to take a Lie algebra homology function. And all these ways of doing this is 0. Okay? So, special case, EP, the graded module, and FPP is a complex. Namely, it's a complex of vector spaces or L modules. Okay? These are homomorphisms of LP modules. So this is a LP homomorphism. Okay, so, right. Okay, so I emphasize, so what this means is that for every parabolic, maybe this was not a thing to do right now, but for every parabolic I've given myself a complex, okay, which can be thought of as being basically giving me a complex of sheaves on the symmetric space, locally symmetric space of that parabolic. And they're tied together by these morphisms, which are just not, which are some extra data. Okay, so they are like some sort of homotopy type data, maybe. Yeah. So there is a notion of L homomorphisms. I won't get into that. Okay, so it's something that you write, and there's only one way once you've made this definition. And there exists a functor. Okay, so I'll write it in a certain way, and then L module, and I'll explain it. Which constructs from every L module, so a combinatorial gadget with those data, it constructs a complex of sheaves on M star. So this is what I call DBQM star, a constructible complex of sheaves. Okay, so as it's written here, it factors through two functors. One is the actual construction is very elementary, and it lives on, so M star has a certain thing called the reductive Borel-Serre compactification, okay, which is, you know, a very natural object, but I won't spend time explaining it. And it also is a compactification of M, and then P is the push forward to here. So Sapir constructed this functor real, which goes from L mod to objects on M bar, and then you push forward to M star. Okay, so I emphasize this is a completely topological construction. It's quite elementary and it's nice. Yeah, but I also, this is not a triangulated category. Okay, so this is just a category, and there's a functor. Okay, so then, okay, so plus can introduce. Okay, so I have to say something more about this. Okay, so L mod is the category of complexes. I'll just say this in word. Category of complexes, for those who have maybe seen some of these things, of a natural DG category. Okay, so that's just, nowadays these things are becoming more widespread. Okay, so so the key point is the following. So let me state the theorem. So there exists a derived category. Let's call it the bounded derived category. Okay, so let me tell you what it is. I have a functor to sheaves. Let's take this functor, actually, this is the right one. And I can just simply say that I go modulo the relation where two L modules become the same if they become quasi-isomorphic over here. That is a true thing, but that's not how you have to construct it. You have to use this DG machinery to construct this properly, and it's a bit, well, it's quite elegant once you get, but it'll take time. Okay, so I emphasize that L modules are simple things. You just have a graded L Levy module for every levy, and then there are these morphisms which tie them together in some natural way. But the moment you have LP modules, LP contains the split part of the center. Okay, and so you have a semi-simple, everything is assumed semi-simple, so, well, yeah, you have a semi-simple AP action on EP. So that means you can truncate it by Lie theoretic weights. Okay, so there is a naturally defined, I'll define what it is. Let's say DB, okay, so I'm going to run out of notation. So this is nu is a weight on the split parabolic. Okay, what I denoted A naught check before. And this is the case, EPs. So this is a collection of data such that the weights of AP on EP are greater than or equal to nu, or rather nu restricted to AP, because nu is a weight in A naught. Okay, so we've just produced one half of a T structure, and the other half of the T structure, which is not greater than nu, is the same thing, not greater than nu. Okay, it's not the same as less than or equal to nu, but okay. Okay, so now I will just quickly state the real theorem, and which I hope will justify itself.
A
Sorry? Yes, so A is a split torus, and I'm assuming that, it's acting on a complex vector space. So there are characters, right? The character group of A has a partial order. So this is partial order with respect to the positive cone, the usual thing, right? In the positive cone starting at nu. Okay, so the theorem is that there exists a diagram. Okay, so maybe this was L modules. Okay, so this is what I called curly D, which I'll rewrite again as dBm m star. This is the forgetful functor which I just erased. And this is the functor that we saw on the previous board. So there exists a diagram, and tau is a triangulated functor and takes and is T exact for the two T structures here. So that is dB L mod less than or equal to nu, greater than or equal to nu, and the other guy not greater than or equal to nu, and the Morel T structure on curly D. I'll have to say one thing here. For A, okay, so if there's time, I'll make this. There is an explicit dictionary between integers. Okay, so I forgot to say this. Okay, so I'll cheat a bit and tell you what this is in a second. Okay, so what's the point here? The statement, there are two statements in this theorem. One is that there exists a triangulated functor from these combinatorial gadgets to your mixed objects. And the second is that, and it has this property, that it lifts that functor, which is a topological functor, to this thing. And the second property, which is what implies all the previous results, is that it is T exact for the T structure that I just introduced over here, and that one of Morel's T structures. So here there is a slight point that Morel's T structure that was used there depended on only one integer. But once you have T structures on objects on a space, you can always glue T structures for different strata. And this is a glued T structure, which is the gluing is determined by this correspondence. Okay? So I'll just say this is not, I won't go into precisely what this guy is. It's the glued version. You glue all the structures according to any function from the strata to the integers. You glue these for different DWs. Okay? So this is the theorem, and this implies all that was said before. So there are kind of two, okay, so I will just say in words what this involves. As I said, there are really two statements here. One is that this is there exists a triangulated functor. So the existence of T is quite interesting, and so this uses a lot of older results of Bogos and Wildeshaus. Also, some of those were proved by Harris and Zucker, but we don't need all that. And in some sense, the ideas involved there, including specialization, all go back to a paper of Rappaport and Loengha. And the second thing is the T exactness, and this uses a different, well, there are two ways to prove this. One is that you just find generators for these categories, triangulated categories, and so, okay, I didn't say this, but these are also triangulated subcategories, it's obvious. Yeah. So there are generators for these categories, and you have to prove that those generators go into that, and that uses a lot of, again, earlier work of number of people, which somehow understand the geometry at infinity of these varieties and the local Hecker action and all that. Okay, so this is the this thing. Okay, so of course, maybe I should also remark that yeah. Okay, so this is a very explicit thing. I'll just say what this is so A is a function from the strata of M star. A is a function from the set of maximal parabolics, which are the strata of M star. to the integers, and it has the following very explicit description. If G add is Q simple, then I take my weight nu that these two correspond if nu restricted to, so let's say the maximal parabolics are P1 up to PD, PR, the rank. Nu restricted to AD should be chi sub D to the minus A underline MD plus dimension of MD. Okay, so what I have in mind is that M star is a union of, is M union certain strata which are MD, and D runs between 1 and R. Because this is a maximal parabolic, there is a distinguished AD. So MD corresponds to PD which contains AD, or the levy. And there's a distinguished positive generator. So I just want to say that there is a very explicit formula. It's easy to compute in any case. This equality? Yeah. Okay. So if you take a maximal parabolic, so take a stratum, it means there's a maximal parabolic. It means that its character group of the levy is one dimensional. This is a generator. Yeah. So nu restricted to that thing, nu is a weight on A naught. So when you restricted that, it is exactly this power of the generator. This is A, which is the function we want to define, of MD minus plus the dimension of MD. Maybe it would be useful to clarify that the half sum of positive roots corresponds to the A is constant. No, Q simple though. So I define it by saying that the action on N, yeah, Q simple, yeah, yeah. So if you take the special thing rho, it becomes the constant function whose value is dimension M, because here you get dimension of this minus maybe, yeah. U is minus rho naught. Okay, it's a very explicit function. Okay, it's not really the tricky part. Okay, anyway. Okay, so yeah, I want to emphasize that this. So right, as I said, that maybe the technical part, it's all technical, but the technical part that's new is that by using some kind of DG methods, you're able to construct this triangulated functor T, and then the T exactness follows from as it did if anybody has ever looked at this paper, which has sat on my homepage for a long time, or heard one of the talks that I gave on it. Well, I haven't given many, but I think one person here maybe have been there. So that part was, that was what was missing. Okay, so maybe I can give one, I'll mention, okay, so I'll just take 1 minute more maybe. I'll mention that I haven't really maybe, by going into this technical details, I haven't really sold you the spectral sequence. But let me just remark that it gives a quick proof of the following theorem, which I maybe should call folklore, but it's the fact that the weight graded pieces, I mean this is known, was certainly known to many people that this ought to be true. The weight graded pieces of HIM give no new pure objects, pure structures, i.e. they already appear in the boundary intersection homology of boundary objects, of boundary strata. Okay, so although this is folklore, I better give some attribution. So, I mean, I think this has been known to many people, in particular Laurent Clausel for a long time. But maybe there was, I mean, my first version of this paper proved it in Hodge structures and Hodge-de-Rham structures. And then there was a paper by Johansson and Thorne where they, Johansson, sorry? Yeah, and Thorne, yeah. I'm not sure if it's double N or double S. Okay, so Johansson and Thorne where they proved it for for unitary Shimura varieties in the Galois setting by very different arguments. Well, not very different, but different arguments, using a lot of known information about those things. But the point is here, you can prove it again if you work carefully in mixed realizations, you can prove the full theorem, right? As it should be, yeah? And it's a consequence of some of this formalism. Okay, so the other point I'll just make is that this, I think, sets up, this is where maybe the study of this cohomology really starts, in the sense that one has to, as I said, hopefully fix isotypes in the co-limit and look at these Hecker isotypes for a given pi, and a special case which can be treated quite thoroughly is the trivial representation because in that case Franke's results on the analytic side can be translated fairly nicely in this discussion to, you can say a lot of things about it. Yeah, for example, this is entirely mixed state, not surprisingly, and so maybe the trivial representation, and if M is unramified like AG, it's unramified and all kinds of stuff. Okay, so yeah, okay, I'll stop here then.
Question?
Yeah.
I had the impression that N modules are constructed by Safer.
Yes.
Yeah.
I put it, yeah.
Even in cases which are not Hermitian, is that correct?
That's correct, yeah. So this is perfectly general, this setup, this combinatorial setup, yeah.
But so
I'm-
how far can you do? I mean, so here we have M star, so obviously you are assuming that the situation is Hermitian.
Yes.
Assuming it's not, what can you do
Oh,
in this direction? You agree that the previous things can remain?
so this exists, right? I mean, this Saper already constructed this. Although, okay, he doesn't talk about the derived category, but he clearly knows what's going on.
Except it's probably not it's a different application.
Yes. So right, it's this. Sorry, it's just this part of the diagram, right? And I don't know. I mean, somehow here the main point is that we're lifting this functor to an algebraic category of, a more algebraic category of objects. So I'm not sure what one would want to formulate. In some sense, in the non-Hermitian case, there is no God-given M star, so to speak. There is no sort of canonical smallest minimal compactification or something. That it does basically, the reductive Borel-Serre seems to be the right place to work. Yeah. And so this construction, I mean, of course, Saper introduced these for a good reason. He proved this conjecture of Rappaport, which is quite interesting. I mean, I'll just make a sort of quasi-philosophical remark that this map is kind of very interesting in the sense that, okay, so this is an algebraic variety, singular. This is just a space. Yeah, it's not even it's a kind of it's a space, topological space. But this behaves very much like sort of a minimal resolution of M star, but so for example, the fibers of this map have weight 0. Yeah, so you expect many phenomena on here can be seen over here because somehow it somehow doesn't see weights. I don't know how to put it in a more precise fashion, but I think there's a lot to be said even in the algebraic case about this map. That's another direction, but this is some. So, for example, Saper used to prove Rappaport's conjecture that the intersection complex here pushes down to the intersection complex here, which is a really it's kind of very hard theorem, much harder than the Zucker conjecture actually, and it's really. But I think there's good ways to simplify that and all that. But yeah. So,
With this construction, can you see directly that you get a pure Hodge structure and the
that's kind of, I mean, I think we take it as a given. That's sort of, that's built into the, So the question was whether we can see using this construction that the Hodge structure on intersection homology is pure. I think that's kind of built into the behavior of weights. So
But you do get it.
no, I mean, yeah, but I mean, it's sort of built in from the beginning. So I mean, it's kind of, I don't think it sheds any light on that.
Yes, the larger question is, once you have this, you hope to understand the factor filtration, but that's a very tall order, I suppose. And if you do, then you understand completely the weight filtration.
That's as you said, it's a tall order. So yeah, but okay. I mean, I can give you one. Yeah, actually, this is related to. Sorry. Okay. What Yanis said before. I mean, I just said that the spectral sequence. Once you have this geometric description. Yeah. Okay. So this is related to your question also. So this spectral sequence, the Hodge structures, Galois structures, they're pure. They're direct sums of pure objects, but there are different weights involved. But there's no extension data here. Okay? So in particular, one piece is this pure object. But there are no extension data involved. So it is a simplification of the problem. So another application of this, which I didn't have time to mention, is that one can show that in the regular highest weight case, so E has regular highest weight, there are no interesting, all mixed realizations in this will split. Assuming the whole Arthur package is known. So, but that's known in many, many situations, right? So the idea is a very simple thing. You want to split it using Hecker operators. Arthur controls the Hecker parameter. If you have parameters, you can control the eigenvalues enough so that it will split. And it's very useful. It sets up an easy induction because you just need to separate the E1 term from the boundary from the main E1 term. It's not hard. Okay? So therefore that's an unconditional statement for many, many groups, and it's certainly true, therefore, and that fits with, I think Harder had found this in many small examples, SP4, U21, etc. So as I said, this is useful for proving kind of properties of either a whole Hecker isotype or general properties, and those don't seem to be really so easy to prove using the boundary spectral sequence and things like that. So general this thing, yeah. On the other hand, if you want to construct examples related to values vanishing of L functions, I don't know that this simplifies matters, but as I said, the analysis of this summand is very, very clean this way.
Any further questions? Okay, no further questions.